Hello everyone, this is chapter 8.4 where we'll discuss Bayes' formula. And before we get there though, I want to take a look at this example because this will actually set up the scenario for Bayes' formula. So here in this example you can read through it, but there's two urns. One urn has 1 red and 3 green balls, the second urn has 3 red and 2 green balls, and there's a die. Gets a little more complicated of course. And if you roll the die, 6-sided die, and if it's 1 or 2 come up, then you draw from the first urn. So just to give you like a scenario, to give you visualization, I guess. We have urn 1 and urn 2. Now in urn 1, there's 1 red and 3 green. So they put like a G here for green. And for the second urn, there are 3 red, 1, 2, 3 that are labeled R, and 2 that are green, so 2 Gs. Now, the probability of rolling 1 or 2 is 2 out of 6, so that's 1/3. So we have a 1/3 chance in drawing from the first urn. So probability of drawing from the first urn is 1/3. I haven't even read the rest of the question, I'm just kind of speculating. And therefore, the probability of drawing from urn 2 would then be the complement of 1/3, which is 1 minus 1/3, which is 2/3. Or you can think of it as, if you don't roll a 1 or 2, you roll a 3 through 6. There are 4 numbers there. They each have, the same likelihood of occurring. So 4 out of 6 total reduces to 2/3. Anyways, let's continue reading then. So yeah, so if 1 or 2 comes up, we draw from the first urn. Otherwise, we draw from the second urn. Okay, good. Right. So if the ball drawn is red, what is the probability that it came from the first urn? So all we know is that we drew a red ball and we want to figure out, did we draw from the first urn or from the second urn? Now this is a different type of example compared to the probability problems we saw in the previous sections, because here we're asked essentially to read the past from a future prediction kind of. So depending on what happens now, can we determine the probability of what happened in the past? So let's see. So we want to find the probability that it came from the first urn, so probability of U1, given that the ball is red. That's what we're trying to find out. Now, luckily for us, we have a formula for given, one given the other. This is conditional probability. So this is a probability that it is, let me see if I can write this. The probability that it is in the first urn and that it's red, divided by the probability that it's red. Good. So far it's not too bad, I guess. Now what? Well, now things get a little more difficult to figure out ahead of time. We know this much, but do we know anything about the probability that the ball is red? Well, the probability that the ball is red, it seems to be there are 4 out of how many balls total, but it kind of depends what urn you pick from because each urn has a different likelihood of occurring. So you can't just say that it's 4 out of 9 or whatever the case may be, because this has 1/3 of a chance of occurring where that has a 2/3 chance of occurring. But then you may think, well, why don't you just multiply those possibilities, so 1 out of 4 and 3 out of 5 with these likelihoods. And that's one way of doing it, to be quite honest. I think that'll probably work. But instead what we're going to do is we're going to expand the bottom. So what I'm going to do is I'm going to say the bottom, so let me just write it over here. The probability of being red depends on which urn we chose it from. So let me just say this. If it's red, either it was red and it came from the first urn, so it was red and it came from the first urn, or, meaning union, so keep that in mind, union, it was red and it came from the second urn. So if that's the case, then we have to take the probability of this plus that. Now notice these are definitely mutually exclusive events, so we don't have to worry about the probability of the intersection, because if you drew from the first urn, that means you didn't draw from the second urn. They're mutually exclusive events. They're disjoint, in other words. So this is the same as a probability of R intersect U1 plus the probability of R intersect U2. Okay. Perfect. So now that we have that settled, well, we need to find out each of these. Now the probability that it is red and that it's in urn 1, that also is kind of hard to find. So it kind of seems like we're trying to expand, but then it just keeps getting worse and worse and worse. So I run out of space here, but I'm going to erase the question. I'm going to shift up the results. We just found all this basically above, and then we're going to continue. So here it is. It shifted things up, and it's a little prettier of a picture to look at. Anyways, so let's see. So we have figured out that the probability of drawing from urn 1 is 1/3 and urn 2 is 2/3. Also, we expanded this out to this much, but to find each of these seems kind of hard. How do we know the probability of it being red and that it's in urn 1? Well, if it's in urn 1 and it's red, then that means that it's 1 out of a total of, well, that many balls in urn 1. But the probability of urn 1 occurring, that I think may be the problem there. But you know what? Let's do this. Let's kind of think for a second. We're trying to find the probability of urn 1 given that it's red, but can we find the probability that it's red given that it was drawn in urn 1? And the answer is, I believe we can. This is actually what I was talking about here. Because if it is in urn 1, then that means we're looking at this one only. The probability that it's red, that the ball is red, given that the ball is in urn 1, well, there are 4 balls in urn 1, and there's only 1 red ball. So this is 1 out of 4. Similarly, the probability that it's green, given that it was in urn 1, is going to be 3 out of 4. The probability that it's red, given that it was in urn 2, is, well, let's see, how many balls are in urn 2? There are 5, but only 3 of which are red. So this is 3 out of 5. And probability that it's green, given that it was in urn 2, is then 2 out of 5. Now, the green ones, honestly, I don't have to calculate, but I'm just doing that just so we can kind of see how you do those sorts of things. All right, so now what? Well, now we actually have a product rule that we can expand a intersection probability with. So for each of these, I can say that this is just the probability that it is in urn 1 multiplied by the probability of, well, red given urn 1. So if you don't remember this is actually something we discussed in the previous section that has to do with, well, conditional probabilities, of course. It's basically this rule here, only we're multiplying by the denominator, and if these were reversed, so then this wouldn't be R, that would be U1. So that's how this comes about. Similarly, so let me block this off a little more. For the second one, this is the probability that it is in urn 2 multiplied by the probability that it's red, given that it was in urn 2. And we know all of these. So in fact, let's see if we can do this. So the probability it's in urn 1 is 1/3. Multiplied by the probability that it was red, given that it's in urn 1, we know that's 1/4. Plus, the probability it's in urn 2 is 2/3. Multiplied by the probability that it's red, given that it was in urn 2, is 3/5. So it's almost exactly what I said at the very beginning. Just find the probability of each one and multiply them by each of their likelihoods of being in those urns, add those together, and that's your result. That's basically what Bayes' formula kind of says, but remember, this is just for the denominator. We haven't even discussed the numerator yet. The good news, though, is that this right here coincides with the numerator, if you think about it. So this result here is going to be the same as numerator. So let me note that. Same as numerator. Okay. So now these cancel out. This is 1/12 plus 2/5. We can find a common denominator, multiply this by 5, multiply this by 12. We get 5 plus 24, which is 29/60. All right. And yeah, so there we go. So now that means in total, the probability that it's in urn 1, given that it's red, is equal to the numerator, which is just 1/12. All right, so far so good. Divided by the denominator, which simplified to this, 29 over 60. Now, of course, if you multiply the top by the reciprocal of the bottom, you get some cancellation. So 12 goes into 65 times, so our result is then 5 over 29. Awesome. So there's a 5 in 29 chance of the red ball drawn being from urn 1, which makes sense because there's a small chance of drawing red from urn 1. There's an even smaller chance, well, maybe not even smaller, but there's also a smaller chance of drawing from urn 1 opposed to urn 2, because urn 1 has a probability of 1/3 from being drawn from, where urn 2 has a probability of 2/3, which is double that. So I know this is kind of a complicated example, but there it is. At the same time, the question was it had a follow-up question. And the follow-up question was, what about drawing from urn 2? So if we made this urn 2 instead of urn 1, well, I suspect that the answer will just be the complement of this. Because either, if we drew red, either it came from urn 1 or it came from urn 2. And there's no case where it could come from both, because they're mutually exclusive events. We either draw from this or from this. We don't draw from both. So with that being said, if we drew from urn 1, the probability is this. If we draw from urn 2, the probability has to be the complement of this. Otherwise, well, I guess that there is no other case, because again, those are the only two possibilities. Either you drew from urn 1 or from urn 2. So if it's not this one, it's the other one. So I suspect that, and you can check for yourself, but what I'm saying is I suspect that the probabilities, this is for the follow-up part. So the follow-up question was, what about the probability drawing from urn 2, given that the ball was red? So I suspect that the probability drawing from urn 2, given the ball was red, based on the logic I just spoke of, is the complement of this, which is 24 over 29. So notice I'm just doing 1 minus that. So 1 minus a fraction is just, well, bottom minus top over the same denominator. And you can check this for yourself by replacing all u1s with u2s. This denominator will still be the same. So in fact, what you kind of see is that this guy right here, the second term would be the numerator now. So this actually helps more, because the second numerator, or the second term, which is now our numerator, was 2 over 5. 2 over 5, So it'd be 2 over 5 multiplied by this. So let's see. If it was 2 over 5, let's see, 2 times 60 is 120, and divided by 5 is indeed 24. So you do get 24 over 20. So I just did kind of a quick calculation in my head to make sure that this is indeed correct. But again, because it's the complement of that, it should also line up too. Anyways, I'll stop rambling on. Let's move on to actually discussing what Bayes' formula really says, and we'll see how we could have used it just to start the problem right away. Alright, so here's Bayes' formula. So it says let u1 through un represent n mutually exclusive events whose union is the entire sample space. So you think of u1 through un being these sets that have nothing in common, that all together combine to create the entire sample space. They amount to the entire sample space. Alright? Let E be some non-empty event that is contained in S. So it may overlap with some of U's, it may overlap with all of U's, who knows. Then the following is true. So the probability of U sub something, so U1, U2, or U any number through N, given E is this. So I'm just expanding this out, very similar to how I expanded out for the previous example. Now, I don't want to say that the last one is necessarily the one we'll be using all the time, but it kind of is. Really, it depends on the situation. In fact, if you know the probability of E already, then this is it, and you're done here. But in reality, I'm going to box the last one, because the last one I think is really where Bayes' formula kind of shines. So you'll see kind of the usefulness once you know the probability of each of these conditional events, then multiplying to the probability of being in each of the sets themselves, u1 through un, adding those together after multiplying will give you the denominator, and one of those would have to be the numerator, just like we saw for the previous example. Now I give a visual here. Oh, also I is just any number between 1 and n. So it could be u sub I, u sub 2, u sub 3, any of these u's really. I know it seems weird because we have like finitely many u's, but I'm not saying what the last one is. So it could be that there are 12, it could be that there are only 2, like in the last example. So n just represents the amount that there are. Well, anyways, for this Venn diagram, it looks kind of funny, but the Venn diagram, usually we have S as being our sample space, and it is the same actually. So S is the entire thing. So imagine this S represents the whole box here, but it's broken up into these smaller rectangles that I'm labeling by U sub something. So U1, U2, U3, all the way to UN, and notice they don't overlap. So they're mutually exclusive events that altogether compose to amount to this entire sample space, S. Now, given that there is some event that lies in S, it may or may not intersect. Let's just assume it does intersect all of them, like this. And that event is, of course, E. Now, if it doesn't intersect one of them, but intersects the other ones, then that means the probability of U, whatever it wouldn't intersect, and E. So since they would be mutually exclusive because they don't actually intersect, then one of these would be 0. So basically it's a case you wouldn't want to consider, is what I'm trying to get to. So this visualization here should kind of explain what each of these pieces kind of means. So notice that we want to find the probability that it is in U something given that it was in E. So let's say we want to find the probability of U1, just to make it simple, given that it was in E. So if it's in E, then we're dividing by E, but the probability of E, the amount of things in E, but what we're dividing by as far as the numerator goes would be, the probability of things in U1 only. So the things that are in U1 and also in E would be this right here, this shaded region. Dividing that by all the elements in E. So that's basically just describing this first part here. But this first part here for the numerator is just the same as, so notice we can write E as the intersection of each of the U's with E's, and that's just each of these subparts of the rectangles. So each of those subsections that amount to E. So let me just shade that in blue. So this part here is just the intersection of U1 and E. Here, this is the intersection of U3 and E, and all the way until we get to the intersection of UN and E. So this shaded region is all the ones in between. All right. And we know since those are intersections, we can write them as these, as the probability of E1 given U1, or E given U1 times the probability of U1. So there are visualizations of explaining why this works, but I think if we just understand the expanding using the product rule, that's really all it is. Also, what you can do to help the understanding of what Bayes' formula really says is you can actually use probability trees, and you'll start to see that it's really just amounting to multiplying certain branches for the numerator and then for the denominator. So there we go. And now we're going to move on into one more example of Bayes' formula, but in this example though, we'll just be using Bayes' formula right away instead of thinking about it and expanding. We already have this tool, but we can use it as a hammer to basically solve the problem right away. So let's see if we can do that right now. All right, so for this example, it's an application problem. I know it seems a bit wordy, but let's just get right to it and read it. It says a company produces 1,000 refrigerators a week at 3 plants. So there's plant A, plant B, and plant C. Plant A produces 350 refrigerators a week. Plant B produces 250, and Plant C produces 400 refrigerators a week. Production records indicate that 5% of the refrigerators produced at Plant A will be defective, 3% of Plant B will be defective, and 7% produced at Plant C will be defective. All refrigerators are then sent to a central warehouse. And now finally the question asks, if a refrigerator at the warehouse is found to be defective, what is the probability that it was produced at Plant A? So now we're going to take this to the board, and I'm going to summarize this question with a few key points. So let's take a look at that right now. Right, so after reading that problem, here are the key results. So there are these amounts for each of the plants. So there's 350 produced at Plant A, 250 produced at Plant B, and 400 produced at Plant C. And these are the probabilities, basically, of the amounts being defective. So 5% are defective at plant A, 3% are defective at plant B, and 7% are defective in plant C. So now what we're asked to find the probability that it's in plant A given that the refrigerator was defective. So remember, from what Bayes' formula really tells us is that you can essentially just swap this part of the conditional probability for the numerator, multiply that to the one that's given, so the probability of the given set would be A in this case, and the denominator will just be a sum of terms that basically are this, but instead of A, it'll be A through C in this case, because those are the sets we have to deal with. So it's going to be the probability that it's defective given that it's in A, multiplied by the probability of A, added to the probability that it's defective given that it was in B, there we go, multiplied by the probability of the refrigerator being from plant B, and then the same thing for C. So probability defective given that it was in C, multiplied by the probability of it being from C. Perfect. Great. So now, can we find the probabilities of each of these? Well, let's see. I think we can. But first, let's take our eyes to the defective ones. So what is the probability that a refrigerator is defective given that it is in plant A? That is literally this. In fact, each of those are literally these. So if you look at these percentages as decimals, those are the probabilities. So there is a 0.05 probability of a refrigerator being defective in plant A, given that the refrigerator was produced in plant A. For plant B, it would then be 0.03, and then C would be 7% in decimal, which is 0.07. Now, what is the probability that a refrigerator comes from plant A? Well, there are 350 that are produced in plant A out of 1,000 total. So 350 divided by 1,000. The nice thing about dividing a 3-digit number by 1,000 is that you just put a decimal in front. So this is literally going to be 0.35. Probability of B will be 0.25. The probability of C will be 0.4. So now let's just multiply and add. Just like that, and let's see what we get. So plugging all of this into my calculator, I got about 0.33. So that is the answer, and that's it for this problem. But I did mention something about probability trees, so I'm going to show you a visualization using probability trees and how you would solve this type of problem with probability trees. So let's see. We need a branch for each. Well, first we need to figure out which plant we're coming from, and then if it's defective or non-defective. So there are 3 plants. So there's plant A, plant B, and plant C. And then from there, either it is defective or non-defective. So let me write D prime for the complement of defective, which would be non-defective. So same thing here. There's either D or D prime for B, and for C there's either D or D prime. Perfect. Now what? Well, now, what Bayes' formula from a probability tree perspective really says is that if you want to find the probability that it's an A given that it was defective, you find that probability first by multiplying, and then you do the same thing for all of the defective ones. So, because it could have came from B or C, but since we want it to be defective, we're going to multiply the branches that only lead to D for defective. So first we need to find these probabilities, of course, and we kind of already did here. So the probability that it's an A is 0.35. Probability that a refrigerator is produced in plant B is 0.25, and for C it's just 0.4. Just like that. Now the probability that they're defective are just those percentages there as decimals. So 0.05, 0.03, and 0.07. Now the D primes you don't really need to know, but let me just tell you that it's just going to be the complements of those. So D prime for A would be 0.95, this would be 0.97, and that would be 0.93. I'm not going to write it though because it'll be too cluttered of an image. Anyways, so again, what Bayes' formula really tells us to do is the one we want is A given defective, so we're going to find the probability is defective given A, which is this times this. That'll give us the numerator, and there it is. So the numerator here is that's the thing I didn't actually say. But when I was doing the calculation, I was letting this part here be the same as this for the numerator. So this is 0.05 times 0.35. So I typed that in, but I just didn't explain it earlier before I came up with this calculation. So if you're wondering where I got this from, is because the numerator was the same as the first term in the denominator. So there we go. And for the denominator, so this part's the numerator, and for the denominator, it's all of the possible branches that lead to defective multiplied. So this one included, also this one, and also this one. So if you multiply these two, these two, add those results together, that'll be the denominator. And then the one in red is the numerator, and there you go. So it's really just the same as what we did here, but from a visualization using the probability tree, which I think will help because it's less to remember as far as formulas go. Anyways, that was it for 8.4. Again, we didn't really do too many examples here, but to be quite honest, it's just one formula. So in some sense, 2 examples for one formula isn't actually too bad. But again, that was it for 8.4. I'll see you in the next video where we'll discuss 8.5. It's going to be a lot of fun. I'll see you all then. Thanks for watching.